Our goal of this lesson is to be able to understand and identify the extrema of functions on both open and closed intervals. We're going to get started with a brief introduction. A lot of things in calculus is directed towards being able to figure out how does a function behave on an interval. Some of the questions we may ask is, does the function have a maximum or a minimum value on that interval? This question, or rather these questions, will be answered in section 3.1 of us finding maximums and minimums, finding extrema. Also, we may be interested in where the function is increasing or where it is decreasing. We will learn how to use calculus. More specifically, we will learn how to use derivatives to be able to answer all four of those questions over this lesson and the next one. So here we have our first example, and we are looking at functions over different intervals. All of these are examples of the same function. They're all x squared plus 1, but notice that the last one's a piecewise one. We'll get to that one in a second, but it's still the x squared plus 1 parabola. And what we're looking for here is, does the function have a maximum and does the function have a minimum on the interval that we're talking about specifically? So in the first case, we're talking about the closed interval -1 to 2. So notice that we're including the endpoints of -1 and 2. Now on that graph, the highest point that we see is at 2, 5, where we have our maximum, and the lowest point that we see is at 0, 1, where we have our minimum. Now, if we adjust the interval and no longer include both of the endpoints, right? So now the interval is open, we still have a minimum at that dip right there at 0, 1, but we no longer have a maximum. Right? So when we're on an open interval, we can't say, oh, we definitely have both, because this is an example with an open interval that does not have a maximum. Now here we are back to a closed interval, but we have adjusted the function so that it is no longer continuous, right? The function's not continuous right here at x is equal to 0. And if you think back to section 1.4, we learned that a function is not continuous if the reason this function is not continuous is because the limit as x approaches 0 of g of x does not equal g of 0, right? The limit goes to 1, but the function value at 0 is 2. So that's why that function there is not continuous, because with this jump that's happening in here. So we have this discontinuous function, and now it does not have a minimum. It has a maximum, but it doesn't have a minimum, even though we're still on a closed interval. So these examples, what they do is hopefully give us some kind of sense of what has to happen in order for a function to have both a minimum and a maximum on a closed interval. And what has to happen is the function has to be continuous and the interval has to be closed. If the function is continuous on a closed interval, then we will be able to find both a maximum and a minimum. Let's look at a quick example of that. So I have gone to Desmos and I have typed in our equation, and because we are only looking for extrema on the interval from -1 to 3, I've added in here in curly brackets that interval from -1 to 3 so that we only see the piece of the graph that stays between those x values. On that piece of the graph, we can see that we do have a maximum and we also have a minimum. I highlighted those points on Desmos before I took this screenshot. You can just click on the graph and it'll show you what those values are. And these x values here are approximate x values. They look like they have been rounded, these x values here. So one thing we are going to do in this course, in fact in this lesson, is we're going to figure out how can we find the exact values of those x values rather than just decimal approximations for them. So how can we figure out this here, a rational form for those answers? We will be talking about relative extrema. And relative extrema happen when you are on an open interval, so say between these two x values, and you can find a highest point. Or similarly, when you are on an open interval and you can find a lowest point. Generally speaking, the relative extrema of a function are the hills and the valleys. You may hear a relative maximum called a local maximum. You may also hear a relative minimum called a local minimum. One thing very important about these relative extrema is that we have to be able to find a neighborhood around it in order for it to be a relative extrema. So we do not have relative extrema at endpoints. So we've seen examples before up here where we had a maximum. This is not a relative maximum. That would be an absolute maximum. It's the absolute highest point on that interval. This we could call a local minimum as well as an absolute minimum because there is a neighborhood around it. It's not at an endpoint. So we do not have relative extrema at endpoints. So there's a couple ways that we could have these relative extrema then. I'm going to consider two different scenarios. We could have relative extrema at hills and valleys that are smooth and rounded, just like we did here in this example. We have a smooth rounded relative maximum and a smooth rounded relative minimum. Same here. Smooth hill goes into a smooth valley. Or if it's not smooth, we could also have a pointy hill and a pointy valley. So here's an example of a function that has several relative extrema, has relative minimums at these two dips in the graph, there, and it has one relative maximum right here. So the two different scenarios that we're talking about are smooth and rounded versus sharp and peaked. And now we're going to go investigate, well, what happens to the derivative at these places? What is the value of the derivative at these points here? Example 3, we are given, or in example 2, we are given 3 different graphs, and we are shown where the relative minimums and relative maximum are, and our goal is to find the value of the derivative at those extrema. So we have this function f. We are going to start off and find f prime, and then we're going to see, well, what is the value of f prime when x is equal to 3 at that relative extrema? To find f prime, we are going to need to use the quotient rule. So I've identified f and g. I'll go ahead and find f prime and g prime. And now I can use these to find f prime of x, which is f prime multiplied by g, subtract g prime multiplied by f, and all of this is divided by g squared. Now that we have f prime, let's see what its value is at our relative extrema when x is equal to 3. So plugging 3 in for x, comes out to give us 0 in the numerator. So in the first part of example 2, we saw that f prime was equal to 0 at the relative extrema. Example is the absolute value function. If you remember with the absolute value function, we have to approach that as a piecewise function because it is defined as 2 lines. It is defined as the line of slope with positive 1. Well, I'll start with the line with negative slope first on the left. So when x is less than 0, that is the line negative x. But once x becomes positive and x is greater than 0, that is simply the line x. So we can see that we do have a relative extrema at the point 0, 0. We want to see what is the value of the derivative at 0. In order to do that for an absolute value function, we're going to need to use the limit definition and look at the limit as x approaches 0 from the left of f of x minus f of 0 all over x minus 0. And we're going to need to look at the limit as x approaches 0 from the right of f of x minus f of 0 all over x minus 0. Wondering where that's coming from, take a look back at section 2.1. Example 3, a similar thing is going on here where we're looking at an absolute value function and we're looking at the value of the derivative at that corner. Again, we had to break it up into that piecewise definition and look at the limit as we approached from the left and the limit as we approached from the right. As we approach from the left, the orange line is the line negative x. And f of 0 is simply 0, so we're left with negative x over x, which is the same thing as negative 1. And so this entire limit is equal to negative 1. However, as we approach 0 from the right, we are now on the line positive x. So I'm going to be replacing f of x with just x. So we are left with the limit as x approaches 0 from the right of x over x, which is simply the limit as x approaches 0 from the right of 1, which is equal to 1. And these two are not equal. And these two not being equal implies that the derivative does not exist at x is equal to 0. More specifically, I'll put the derivative does not exist at the relative extrema. So far we've seen an example where the derivative was equal to 0 at the relative extrema, and an example where the derivative does not exist at the relative extrema. Let's see what happens in the last example. Here we have the function f of x is equal to sine x. We can see the two places where this graph has relative extrema. I'm going to go ahead and take the derivative. The derivative of sine is cosine x. And now we're going to evaluate the derivative at the two x values where we have these relative extrema. So we want to know, what is the value of the derivative at pi over 2? Well, let's plug pi over 2 into cosine. And cosine of pi over 2 is equal to 0. Now let's see what is the value of the derivative at that relative minimum at 3 pi over 2. So now I'm going to plug 3 pi over 2 into cosine. And cosine of 3 pi over 2 is also equal to 0. So this example is similar to the first one that we looked at, where we are again seeing that the derivative is equal to 0 at those relative extrema. So these three examples gear us up for our next conversation, which is going to take us into how can we figure out exactly where we have these relative extrema. Well, we kind of have a good idea at this point, because so far we have only seen relative extrema showing up in one of two places. Either they're showing up where the derivative is equal to 0, or they're showing up where the derivative does not exist. And that brings us to the definition of a critical number. A critical number first needs to be a x value that is in the function's domain. So if we have a value that is in the function's domain, we will then take the derivative, and we will look for places where the derivative is either equal to 0 or does not exist. And that will give us critical numbers. So for example here, at this sharp point right here, this derivative would not exist. This graph has a vertical tangent. The limit as we go in from the left and the limit as we go in from the right are both shooting off to positive infinity if we were looking at the derivative, not on the graph itself, but if we were looking at these limits here to calculate those derivatives, we'd be finding a vertical tangent line. The derivative would not exist. On the other hand, here's an example where the derivative is equal to 0, and we have a horizontal tangent line. So both of these c values here would be critical numbers for the function f. And why are critical numbers important? Because relative extrema can only occur at critical numbers. So if we have a relative maximum or a relative minimum, theorem 3.2 tells us that that relative max or relative min is happening at a critical number of the function. So it is happening somewhere where either the derivative does not exist or the derivative is equal to 0. We are going to discuss how to find extrema on a closed interval. We have guidelines here, and we're going to go through these guidelines with example 3. We begin by finding the critical numbers of the function in that interval. Here is our function, and we are working on the interval from -1 to 2. In order to find our critical numbers, we need to find the derivative and look for where the derivative is equal to 0 or where the derivative does not exist. So I'm going to begin by taking f prime of x. Using the power rule, I get 12x cubed minus 12x squared. Now I'm going to look for critical values by finding either where the derivative is equal to 0 or where the derivative does not exist. I will take this derivative and set it equal to 0. To solve this equation, I begin by factoring out the GCF. That leaves me with x minus 1 on the inside of the parentheses. And now I will set both of these factors equal to 0 to find that x is equal to 0 and x is equal to 1. Both of those critical values are in our interval, and so that works. So we have found the places where f prime is equal to 0. Now let's find the places where the derivative does not exist. Well, the derivative here is a polynomial, and that exists everywhere. So it never happens that the derivative does not exist. So in this example, we only found critical values from where the derivative was equal to 0. Now that we have the critical values, steps 2 and 3 tell us to evaluate the original function f at both the critical numbers, critical values, and the endpoints of our interval. So now I am going to make a table, and in this table, I am going to be plugging my x values into the original function f. And the x values that we are going to use are going to be the left endpoint of -1, the critical values of 0 and 1, and the right endpoint of 2. And I'm going to evaluate these x values in the original function f, so I'm plugging them in here. When we plug in -1, we get out 7, 0 gives us 0, 1 gives us -1, and 2 gives us 16. So we have done steps 2 and 3. We have evaluated the function at those values. Now, step 4 tells us that the least of these is the minimum, and the greatest of these is the maximum. And so we have a minimum at the point 1, -1, and a maximum at the point 2, 16. And a graph of this function on the interval from -1 to 2, where we can verify that we do in fact have a minimum at 1, -1, and we do in fact have a maximum at 2, 16. Notice that we had a critical value at 0, and that's neither a minimum nor a maximum. So the converse of theorem 3.2 is not true. Just because you have a critical value does not imply that that critical value is a maximum or a minimum. It could be, but it might not be.